Good afternoon, everybody. I'd like to thank the conference organisers for inviting me today to give this presentation on ambulatory activity in Parkinson's, pushing the boundaries of measurement. I realise that I'm standing between you and a conference dinner, so I'll make sure I don't overrun. For those of you that were in Alan Godfrey's workshop on Tuesday, Alan very nicely set the scene for this measurement, dealing with the more critical features of engineering, if you like, to extract characteristics that are of use for us to apply in the clinical field and in the research field. So just to start with, I'm going to give you an overview of what I'm going to talk about today. Firstly, I'm focusing on Parkinson's disease, so I'm only going to refer to studies that have looked at Parkinson's as a pathological group. I'm mainly focused on the work that we have carried out in Newcastle, so really a process that we've gone through in Newcastle to allow us to apply a more sophisticated approach, if you like, to measuring ambulatory activity in Parkinson's disease. And I'm going to take you through this process. And this slide shows the overview of what I'm going to talk about in my presentation, and you'll keep seeing this overview come up, so it helps to identify where you're at where I'm at within the presentation. So firstly, I'm going to define a measurement framework of ambulatory activity based on macro and micro features of ambulation or gait. I'm going to then move on to the advantages of micro-level measurement and the advantages that they have with respect to their application for discrimination, progression and prediction of pathology with respect to Parkinson's. I'm then going to talk about how we went about extending our measurement framework in Newcastle, using allowing us to move out of the laboratory and taking advantage of a single triaxial body-worn sensor to extend measurement, firstly through talking about validation studies that we carried out, and then extending our measurements to free living activity. And I want to reflect on what micro delivers, but also what macro level features add to that extended measurement framework. So looking at them both in balance. And then finally, I'd like to end with future challenges and really highlighting the need for a unified framework of measurements, protocols and tools. And I'm going to end with some challenges that we're tackling in Newcastle now. So, to begin with, defining a measurement framework. So, my title talks about ambulatory activity, and this is a definition. I'm sure you're all aware of ambulatory activity, but this, in essence, is looking at walking in the context of the real world, the big picture of walking, if you like. And we tend to talk about this in Newcastle as the macro level of measuring gait, people's bouts of habitual walking behaviour that occur in a variety of different conditions. And we can apply a range of different metrics. I'm sure you're all familiar with these that relate to the following characteristics, such as amount, intensity, frequency and duration. So that's just a bit of a reminder. However, if we really just stuck to measuring ambulatory activity, we could be missing some very critical and important features that speak more to the micro level characteristics of gait. These are the discrete characteristics that the individual stepping features that we can extract when we think about quantitative gait analysis. And why are we interested in doing this? Well, gait is a really important, is developing into a really important metric in clinical and research use. And this slide gives us some examples of why. Stephanie Studensky in 2011 published a paper which showed that a very simple model of age and gait speed predicted life expectancy. And if you were below 1 metre per second, then this indicated that there was some potential underlying pathology that put you at risk. It essentially identified that gait speed is a simple non-invasive metric that helps to indicate the underlying health of the individual and waves a red flag, if you like, that there may be some preclinical disease. So this is prior to someone really being even aware of any problems that needs to be addressed. Moreover, Joe Verghese in 2007 also showed that in older adults who were initially non-impaired, quantitative gait dysfunction was able to predict risk of cognitive decline and dementia. And it's also been demonstrated that the trajectory of gait speed precedes mild cognitive impairment. So this shows a robust relationship, if you like, between simple metrics of gait and health, cognition and dementia. This has also led to an interest in what biomarkers and using gait as a surrogate biomarker can tell us about cognition in Parkinson's disease, and equally others are interested in what gait as a surrogate biomarker can tell us about falls risk, and applying this in very specific disease cohorts. And in Newcastle, we have an interest in Parkinson's disease, so we have a real interest in not only looking at ambulation in the big picture, but also what we can learn if we look at more discrete features, stepping characteristics of walking, as well as the larger characteristics. So we wanted to study this in more detail in Newcastle, and to do this we needed to really go back thinking about these broad domains and develop a conceptual model in order to allow us to refine our work. So we took the macro characteristics as I've just described, looking at bouts of walking as a metric and characterizing those during free living. And we also developed a battery of micro characteristics from gait analysis, so a standard gait analysis which looks at individual steps and strides as discrete events and breaks these down to characterize gait. And we considered a model of gait would be one in which it would combine both the micro and the macro features to allow us to have a much more global picture of locomotion, and you could say pushing the boundaries of measurement to really roll these features in together. However, this defines gait being measured under free living conditions and under laboratory conditions. So another feature that we were really keen to try and develop was to be able to explore macro and micro, but to fuse these measures together by identifying micro features of gait analysed during someone's free living activity as well as their macro level characterization. So this just sets the scene for what I want to go on now to talk about and what we've learned in this process of using body-worn sensors, what we learned in this process. So what I'm going to do now is talk about the advantages of these micro features of gait. We're going to ignore the bigger picture first of all and really focus in on this smaller picture and how we've applied this in Newcastle. And just really it's a bit of repetition I know, but just to emphasize that we were interested in using gait in Parkinson's disease as a diagnostic tool. We were really interested in this background of work and how we could take the points that have been learned in older adults and apply that to learn more about Parkinson's disease and to help us in disease management. So we were interested to look at the sensitivity of different gait characteristics as a diagnostic tool, to see if they were sensitive to progression of disease, and to see if there was an effective prognostic tool to predict cognitive decline and falls. It's also important to think about the utility of these measures, and I've just really referred to it, but if we can demonstrate these features applied to different pathologies, in our case Parkinson's disease, then we have measures that have really great utility for use by clinicians, for use in the research context in order to evaluate mechanisms of disease, as well as the impact of interventions. And industry are also interested in these features because it helps them in their early phase drug development trials when they really need early signals of efficacy, as well as being able to scale up and use in multi-center studies to have much more refined measurement from what currently exists. And when we think about what currently exists, well, our measures are fairly rudimentary. Typically, when we're looking at the utility in these settings, you're doing really well if you use a stopwatch. Other scales are clinician-rated scales of severity, and in Parkinson's disease it's the UPDRS, or the Unified Parkinson's Disease Rating Scale. But typically what happens is the clinician will eyeball someone's gait when they walk into the clinic and see how they're looking. So we can obviously do a little bit better than that, and we were interested to take this whole process one step further in Newcastle. Pardon the pun. So to begin this, to begin this journey, we had to start off with a known baseline. So we started off by measuring gait in the laboratory with a gold standard, so we could be confident, if you like, in a set of measures and their utility. And we explored gait in the context of the ICICLE study. The ICICLE study is a programme grant funded by Parkinson's UK, and the chief investigator is Professor David Byrne. And the ICICLE follows patients up from diagnosis through to dementia, and carries out a very deep phenotyping of patients, from clinical assessment to cognition, imaging, neurophysiological markers, and blood-based biomarkers. This allowed us to set up ICICLE Gait, which was a collaborative study at the same time as ICICLE was set up, evaluating gait in the laboratory, falls, and also measuring gait during free living activity, so gait in the wild, if you like. So that provided us with a context to be able to look at gait and ambulation to see what it could provide in terms of understanding disease and patient management. And we did this. We had a large cohort of 120 people with Parkinson's disease and 189 controls that were assessed within 6 months of diagnosis and have been followed up every 18 months since then. And we had some specific questions that we asked that we were asking. We wanted to know if gait discriminated pathology. We wanted to know if it was associated with cognitive impairment, and we wanted to know if it could predict cognitive decline in this incident cohort. But to begin with, we actually had to decide what we were going to measure in terms of gait. I don't know if any of you are really familiar with detailed gait analysis. I'm sure you are, as you hear at this conference. But there are many measures that characterize gait, and we pre-specified 16 characteristics from our own work and that of work in the field. And we're interested to see how these characteristics grouped together in terms of their independence. So we carried out, this is work by Sue Lord, she carried out a factor analysis in the 189 older adults and demonstrated that the characteristics broke down into 5 core domains, which allowed us to have an understanding of the underlying concepts, the constructs that they're measuring, which relate to pace, walking speed, cadence or rhythm of movement, variability of stepping, asymmetry, and the ability to retain postural control while walking. And this allowed us to have a framework of microgait characteristics which we could relate to the underlying pathophysiology of Parkinson's disease to help us understand these characteristics in the broader picture in which we were testing them. Importantly, Sue repeated the factor analysis in the 120 Parkinson's cohort, and the model of gait was retained, allowing us to be confident in that the characteristics and the domains were robust going forward. And what we did was we applied this model to understand gait with respect to our hypotheses. So what we found was that even in, so this is an example of someone with very mild Parkinson's disease. What we found was that even when we looked at somebody whose walking looked like this, and you really, if you used your eyes, you wouldn't be able to distinguish them from a control participant. Already these characteristics of gait. Don't worry too much about trying to understand the gait characteristics around the edge. It's the pattern that you're looking at. The characteristics of gait certain characteristics of gait were already significantly impaired compared to controls. Controls here are indicated by the hatched bar, and you're looking at standard deviations of difference from the control cohort. So that gave us confidence that we had some sensitive measures that could discriminate very early disease from controls. We also looked at our characteristics, our different features of gait, and compared them across different neurodegenerative diseases to see if they were able to discriminate between different disease types. And we compared ataxia, spinocerebellar ataxia, SCAR6, which is a very focal lesion of the cerebellum, mitochondrial disease, 2 variants of mitochondrial disease, which has an impact on the neurological control of gait, the central nervous system, and obviously our Parkinson's cohort. And we were able to look in groups that were either very early, you've just seen a video of a gentleman, very early, a genotype of mitochondrial disease that really has very little impairment, and also ataxia, people that carried the gene for SCAR6 but didn't yet clinically express the deficit. And interestingly, if you just look at the overall pattern, you can see that a very different signature of impairment emerges for these different disease profiles. Moreover, with progression in more moderate disease, we can see that this profile develops over time. So we have characteristics that are sensitive to different disease types, but also sensitive to disease progression, which you remember were some of our initial questions. And what this allows us to stand back and ask is, if you take an overall model of gait and look at the characteristics in different groups, do they actually present with a unique signature of pathology? And this is an area that we have an interest in taking forward. But it underpins an area that we have an interest in taking forward. Now remember, we were interested also in seeing if we could predict future problems in Parkinson's. And in this case, we're looking at predicting the relationship of gait with cognition. So you remember this gentleman in the video and his gait impairment, which appears early. Cognitive impairment is also a very common and early feature of Parkinson's disease, with over 40% of people diagnosed with mild cognitive impairment at diagnosis. Again, work by Sue Lord identified that if you mapped the domains, our broad domains of gait, from the factor analysis with broad cognitive domains, she was able to show that there was a strong and robust relationship between executive function and attention, which are functions of the frontal lobes in the brain. They're the attention, they allow attentional control, and they're almost like the manager in the brain, if you like. Flexible allocation of attention, problem solving, thinking, these higher order cognitive skills. These were related to walking speed and pace, to rhythm, and to postural control. So at diagnosis, we can already see a robust relationship emerging between gait and cognition. So this doesn't tell us anything about causation, of course, because it's cross-sectional data, and we're interested to see if we can use our gait metrics to predict problems in the brain, problems with cognition. And this is early data from Rosie Morris, who's a PhD student in my group, which is preliminary analysis from our 36-month data in our cohort that shows in 50 people, that shows that gait velocity, baseline gait velocity, can predict a change in attention at 36 months, as seen here in the modelling, the linear modelling that you did. Baseline attention, on the other hand, does not predict change in attention. So what we can learn from this is that we have this early relationship of gait and cognition at baseline that seems to evolve, so that gait appears to be a sensitive metric that may be able to predict cognitive decline. And we're going to continue to follow these people up to see if we're able to predict dementia. And it also provides us with a window into the brain to understand mechanisms of gait impairment that are underpinned by cognitive impairment and potential shared pathological correlates. And this is important because it helps us to develop more advanced interventions. So that's a little bit about how useful these very specific micro features of gait are when collected using standard tools for gait analysis in a controlled laboratory situation. But the title of this talk is about ambulatory measurement, pushing the boundaries of measurement. So what I want to do now is really get to the meat of this talk, which is about how we extended this approach and we did this in three ways. Firstly, by validating what we did in the laboratory. Second, and then by moving this into free living environment. And then finally, I want to look at what macro characteristics add to the overall picture. So we had to, first of all, really be and the reason that we wanted to do this is because obviously we needed to push the boundaries of measurement. Is obviously quantitative gait analysis tools in the laboratory are expensive. There is limited access to those tools, and they're certainly not portable. So we were wanting to push the boundaries, as I indicated earlier, by adopting a very low-cost, non-invasive approach to allow us to scale up measurement into the clinic and into multi-centre research projects. If it was going to have any utility, we have to actually be able to do this. And in Newcastle we used a single triaxial accelerometer worn on L5, so a body-worn sensor applied at L5, and we aimed to replicate everything that I've just talked about in the laboratory with our gold standard using this sensor, both as a discrete gait measurement tool that could be used in scripted protocols in the clinic and then into the free living environment. So just to remind you, GaitRight basically measures gait as discrete footfall events. It's an instrumented carpet that measures each individual footfall, and that was our gold standard. Sylvia Deldin and Alan Godfrey are engineers in my team who then led on the analysis of our data to replicate our gait model using the sensor. And they did it in this way. They applied firstly an algorithm by Zylstra to the continuous signal, which is what you're looking at here, our continuous signal from the sensor, and they applied it to detect the individual steps, and they checked the individual step detection in relation to what we were detecting with GaitRight in order to be confident that we were accurately detecting steps. And then they took this one step further, again, pardon the pun, by fusing an algorithm by McCamley, developed by Claudia Matzer, which allowed then to the individual phases of the gait cycle, the initial and foot contact phases to be identified, and this allowed us to split up the phases of the gait cycle, and in doing so replicate our gait metrics that I showed you in the model that I presented previously. And what Sylvia then did was she looked at the characteristics. So this demonstrated that it was feasible to, what Sylvia was able to conclude from this was she was able to demonstrate that it was feasible to extract 14 of our 16 core characteristics that we were interested in using. She couldn't replicate some of the postural control features because you really need a gyroscope to do so. So this highlights some of the limitations of the body-worn sensor. But what she then wanted to do was to compare the metrics that she derived using these fusion of these two algorithms to the what we called our gold standard. And this is what she found. And I'd like to say that we're not the only group that have carried out this analysis. There's been many of you in the audience have produced papers with this respect, and I'm just highlighting another paper here, and also the data from a publication, that Sylvia's recent publication. And what we can learn is when we compare our gait characteristics, we have really we have very, very good agreement between mean characteristics of gait. In general, we have very good agreement between the mean characteristics of gait and our gold standard tool. So that allowed us to have confidence in the mean measures that we were looking at. However, when we look at variability, so the step-to-step or stride-to-stride variability, this didn't. We had poor agreement, and this has been repeated. This is a common finding in many other studies. Moreover, asymmetry, which is an area that we've really focused on, it's had less interest in the literature, but we are interested in it in Newcastle, also showed very poor agreement when we're looking at replicating our model features. So this left us with a bit of a problem, really. What does that mean? Does that mean that in fact, it's feasible to pull these measures off, but actually they're really not valid? They don't agree with the gold standard. And did that mean that we couldn't use the tool? Well, Sylvia then carried out some work to try and figure out why there was poor agreement between variability and asymmetry. And what she was able to ascertain was, if you take a population of people who have a very clearly asymmetrical gait, as in the case of Parkinson's disease, and you can see the difference in each step here and this clear asymmetry, then in fact there was good agreement in their asymmetry between a walkway and a monitor. However, when you take a group, in this case a control, with very subtle asymmetry, and we can see the subtle asymmetries here in the continuous signal, then there was very poor agreement between a walkway and a body-worn monitor. Moreover, the monitor is detecting much higher levels of asymmetry compared to the walkway. And what Sylvia was really able to conclude from this was that in fact the sensor is a valid tool to measure asymmetry, and also is a valid tool to measure variability. In fact, the problem really lies in the choice of the gold standard. Accelerometers continuously sample a signal of locomotion, and therefore are more sensitive to some of these very subtle deviations, as opposed to a tool that we would use, which is looking at gait as very discrete footfall events. So it highlights the problem of really comparing, if you like, apples with pears. But what it also allowed us to do was to be confident in using this tool as a tool to use in the clinic for scripted assessment, but also to allow us to think that we may be able to use this tool and start to look at discrete gait characteristics collected during free living in completely uncontrolled situations, what we call gait in the wild. I should also add that the descriptive characteristics, when you looked at the descriptive characteristics of all of our gait outcomes, they were sensible. They were within the range that had already been reported in the literature. So we were confident about the descriptive characteristics. It was more the agreement between the systems that was problematic. And I think what this also does is it highlights the strengths and limitations of all tools that we use to measure gait. And we have to recognize that error is present really in any tool that we use. What we need to do is to be able to understand the error in order to be able to interpret our data in the most appropriate way. I've talked a lot about what are very traditional measures to characterize gait based on the phases of the gait cycle. However, there are many other outcomes that people are exploring using accelerometry, and they've been reviewed in this recent review by Hubble et al. Published in 2015, which looks at walking stability measures in Parkinson's disease, and there are a very large range of walking stability measures that have been reported that really are relating to trunk accelerations, the attenuation of accelerations in the trunk and coefficient of attenuation, and the rhythmicity of trunk acceleration patterns, so harmonic ratios and derivations of these features. We haven't looked at this as yet, and to date there's been no comparative analysis of these sort of metrics with traditional gait metrics. And this really highlights that a broader model is needed if we're looking at these micro features. But what the authors of this review concluded was that certainly they also felt there was support for the use of body-worn sensors to measure walking stability in Parkinson's disease. Okay, so moving on. Now I want to talk about how we extended this measurement to look at micro-level characteristics collected or extracted during bouts of walking in free living conditions. What can we learn in this situation when we push our boundaries of measurement further? Well, to start off, why do we want to do that? Well, it's all about gait measurements, and what we measure are very influenced by context. So you'll know that measurement in a lab sometimes can cause people to walk differently simply because we're asking them to wear all sorts of different gear that really doesn't lend itself to normal locomotion, habitual locomotion. Moreover, this recent publication in 2014 showed that when patients are aware that they're being watched by the researcher, then it has a subtle change in people with Parkinson's disease gait, in that they have improved gait performance. Furthermore, if you ask someone to concentrate on their walking, in the bottom video they walk considerably different when they're not asked to concentrate on their walking. And if we're using these measures to understand disease and to detect the changes in intervention and progression, we really need to have a stable measure which is not influenced by the compensatory changes that we might see in a laboratory environment. Of course, a laboratory environment also allows us to, it's a very controlled situation, and it's a little bit like going from A to B along a lovely straight line. If you look at data from a body-worn monitor, which was if you imagine that was our validation study that we carried out of the body-worn monitor to gait right, you get a beautiful clean acceleration signal during 2 minutes of continuous walking, which is, however, the real world is not like that. There are all sorts of obstacles and changes in locomotion required in order to navigate the real world, which results in all of these discrete bouts of locomotion and changes in the signature, changes in the quality of gait within those bouts. And we really wanted to be able to capture and it's important to be able to capture this feature as well, because it's likely that the ability to be able to flexibly adapt in the real world and cope with all of the changes that are coming at you is also important to help us understand the true impact of pathology. And it may be that measuring gait under these circumstances provides us with a more sensitive discriminatory and progression and prognostic tool than measuring gait when someone is allowed to compensate and cognitively control and think about what they're doing. So that's the basis of why there's an interest in measurement outside of the laboratory. We're not the only group that are doing this. Of course, there are many different groups that are interested in this, and many groups that are looking at older adults. I'm really focusing on the Parkinson's population here. So, what do we find when we look at our micro characteristics in the wild? So what is the effect of environment on sensitivity of micro outcomes? And we ask the following question: is gait in uncontrolled settings sensitive to pathology, cognitive impairment and falls risk? And in fact, is it more sensitive in free living data than in laboratory data collected in the laboratory? So first of all, again, you're looking at our gait characteristics derived from the body-worn monitor. We now have 14 features in our domains, and the hatched line is data from controls, and any changes are with respect to standard deviations from the controls, so they're norm changes. And this data is collected in the laboratory with our body-worn sensor for controls and PD participants, and we're able to see that we can discriminate between controls and PDs using a sensor in this environment. However, when we move to the home, and now data is norm referenced to controls under free living conditions, we can see that the gait, many more metrics discriminate controls from PD under these conditions. So it appears that we may have a more sensitive, the environment has a considerable influence, and it may sensitize our outcomes to detect differences under these circumstances. And this is an area that we're certainly working on in the future, and this is an area that other people are interested in. We then explored, remember our relationship between gait and cognition that I showed earlier? We were then interested to see if the relationship between gait and cognition changed when you looked at locomotion in the real world. So this was the original picture that I presented, and when we look at this picture from free living data, micro-characteristics extracted from free living data, what we see is that there is a considerable change. Pace, executive function and attention, features of the frontal lobe, are still related to pace, but it's less of a significant feature now. There's a much stronger relationship of these executive function and attention to variability. Moreover, spatial memory, which is a feature of the temporal lobes, is related to variability. And what this tells us is that this relationship of spatial memory to variability really relates most likely to navigation. So it's picking up the role of cognitive features that are related to the ability to navigate in the real world. Moreover, an enhanced relationship with variability really probably most likely represents the environmental impact of having to constantly modify locomotion to the environmental demands. Whether these are more sensitive predictors of cognitive decline and dementia, time will tell, and this is a question that we're addressing in Newcastle. I said we're not the only group that are interested in this, and I'm just highlighting data from another group that have specifically looked at gait during free living activity in Parkinson's disease, and to show you how they've their model and how they've applied it to address their own questions of interest. So they measured gait during 3 days of free living activity using a triaxial accelerometer, again located on L5. And they described a different model which was combined of metrics, quantity metrics that really reflect our macro type measures, things such as the number of steps and the percentage of time spent walking, the amount of walking, and quality metrics which map onto our micro measures, and they're the measures that are highlighted that look at stability of gait from the review that I highlighted earlier. And they looked at these features only in bouts of 60 seconds or greater. And this is an example of their analysis. They effectively carried out a time frequency analysis where they described the amplitude of the frequencies, the width of the frequencies, and the slope. And what they were able to show was that these were different in Parkinson's disease, here A, and on this lower graph, and controls, which are B on this graph. So you have a different signature of these time frequency domain metrics that they extracted. They carried out a validation study, which was a slightly controlled validation study, but they did some work to really ensure that these metrics had some validity and to give them confidence before applying them in a larger study. And what they did was they used their these measures as an objective assessment of falls risk in Parkinson's disease. So what they showed was that while the quantity measures were similar in fallers and non-fallers with Parkinson's disease, the quality metrics were in fact sensitive to falls risk. And in particular, it was the width of this frequency that was sensitive to falls risk, and in fact predicted the time to first fall. And they conclude that these tools may be simple, low-cost, non-invasive tools that actually could aid detection of very early falls risk in people with Parkinson's disease. And people with Parkinson's disease have a much higher incidence of falls than normal controls, 66%, as opposed to about 30% in normal controls. So this is obviously an area that is of great interest. So I've talked an awful lot about micro features in the laboratory and in the wild, and I just want to summarize this section of the talk. So firstly, quantitative gait analysis is feasible and it's valid in both controlled and uncontrolled settings. We can show that it has sensitivity to the features that I highlighted that are important clinically and in the research context. But it's also clear that it's, in order to derive these characteristics, they're complex and also multifaceted. And there is no, to date, standard outcome battery available to guide choice of outcome measure. Moreover, there's just a few groups working in this area in Parkinson's disease, and whilst our findings are of interest, they have to be replicated in independent cohorts and larger studies. The data processing is complex. I know that Sylvia and Alan in my group have spent an awful lot of time building a processing pipeline to help us deal with this data, and as yet it's still a research tool and not a clinical tool, and some work needs to take place to really start to translate this. But whilst we have some challenges, it's certainly of great interest to industry and clinical research. So I'd like to move on now away from micro features to to macro. Wow, to macro features. I'm just going to keep going. So what have we learnt? So what does the big picture tell us? What does that contribute? I've gone on an awful lot about what the micro picture contributes, but does it actually help if we add this bigger picture of locomotion when we look at the individual bouts of walking and their characteristics? And what studies have shown that, unsurprisingly, people with Parkinson's disease walk less, they have percentage less walking time and fewer steps. And this is in people with Parkinson's with moderate severity. And these metrics are also sensitive to change over time. Seb Shastan and Malcolm Granite extended that macro measurement framework to further, and they extended it to carry out analysis of bouts, walking bouts. So you think about a bout as a metric. They extended it to carry out analysis of walking bouts that looked at the distribution of these walking bouts, whether someone's daily activity was made up of lots of small bouts of walking or lots of large bouts of walking, and also the variability of length of walking bout. So they extended the analysis of the signal to look at to take a non-linear approach to the data. We applied this initially, working with Seb Shastan, to look at the effect of deep brain stimulation surgery on ambulatory activity in advanced Parkinson's disease. And we were able to show that, interestingly, the number of bouts of walking reduced following deep brain stimulation surgery. However, the bout length increased along with variability of bout lengths. And this is important because it really indicates that individuals were able to develop a more flexible pattern of behaviour following surgery, which is more appropriate for daily living. We've also looked at ambulatory activity in our incident cohort that I've been talking about, and here's some data of the differences between Parkinson's disease, this is N equals 89, and controls measured using, in this case it was ActivePAL, a body-worn sensor. And we saw significant differences in our volume and our metrics, and also our pattern and variability metrics at diagnosis. However, taking an even greater, more detailed look at the walking bouts allowed us to have a better understanding of the impact of Parkinson's disease. And looking specifically at bout lengths that were 30 seconds and greater, we were able to ascertain that, in fact, it's these longer sustained bouts of walking that people with PD really have problems with, not the bouts of walking less than 30 seconds, which typically represent activity in the home environment. And that's allowed us to guide our clinical recommendations and give very specific advice for patients. But it also points to the fact that if you're going to intervene, it's this you need to change, not this. Moreover, we remember the gentleman's walking. Moreover, we also were able to identify that that ambulatory activity was significantly reduced. And if you take a look at ambulatory activity with respect to public health guidelines, we were able to demonstrate that we found that patients who walked this well, only 30% of people were able to accumulate 30 minutes of daily activity, and this was in walking bouts greater than 2 minutes. And it was only 10% in people who had slightly more severe disease, and this is within 6 months of diagnosis, as opposed to 60% of controls. And again, this has allowed us to refine our clinical advice to patients to sit less and move more, even in when they're very early in their phase of diagnosis, in the phase of Parkinson's. Sylvia compared some of these metrics in fallers versus non-fallers, both with and without Parkinson's disease, in the context of V-Time, which is an EU-funded Framework 7 study led by Jeff Hausdorff's group in Israel, and we're a partner, we're a clinical centre in the UK. And she was able to show that a mean bout length, so the length of the bout and the variability of the bout, also differentiated fallers from non-fallers in this large population. So the big picture, what does it add? Well, it gives us a global picture of the effect of pathology on gait, a better, broader understanding, and a broader understanding of disease. Whether there's more sensitivity of micro to macro features, we really don't know as yet, and we need to test this further. These metrics are also very useful feedback tools, both for the patient and for the clinician. Moreover, they give us a true test of our intervention and the burden of disease, because, in fact, if we are intervening, we need to see changes at this broader level, not just changes in discrete gait characteristics. So, finally, I just want to identify some future challenges moving towards a unified framework of measurements, protocols and tools. I've referred to a range of different macro and micro measures, and this is only a few of them, as identified in 3 relatively recent reviews. So we have a very complex area with multiple metrics that aren't applied consistently across different groups and across to address different questions. And this is an area where we really need to do some work to harmonise our outcomes. Moreover, there are now a range of different tools being developed for to analyse gait, to analyse timed up and go, lots of different tools that incorporate different algorithms, and so again, bringing together these features is probably important as we move forward. And it may be that having one single device that allows us to collect a range of different types of data is the best option. And this is some work and Alan Godfrey's carried out some work in Newcastle in the context of the LiveWell study to start to explore the utility of a single device applied in this way. We do, however, have some considerable challenges ahead. And they're listed on here, and I'm sure they won't come as a surprise to many of you. And I've highlighted the need for standardised assessment protocols, harmonised outcomes. We need to validate algorithms with respect to age, disease state, and site of application of sensor. We have issues with data sampling characteristics. We don't know which outcomes are more sensitive than the others. We need replication, and we need to understand how to fuse these micro and macro measures and if this will enhance sensitivity. And last but certainly not least, we actually have to communicate effectively with each other as a community. And in doing so, hopefully we'll be able to make some inroads into these challenges. And what I'd like to do now is to leave you with an example of some challenges that we've been facing in Newcastle in order to help us analyse and understand our data. And this is specifically in relation to data sampling characteristics. So, when is about not about? This is what Alan Godfrey would say. So if you look at these three traces, some algorithms will segment walking bouts, and there will be no stationary period allowed within that. So they'll segment every individual walking bout if there's a period of time when someone's inactive. This, and in this situation, you would have 3 bouts of walking. If a 10-second stationary period of inactivity is allowed in analysing the signal, that would mean that we'd have 2 bouts of walking, because it would discount this. And if 20 seconds was allowed, then we'd have 1 bout of walking. Now this clearly has implications on the metrics that we measure. And here are 2 examples. If we look at the sensitivity of gait to discriminate Parkinson's disease from controls, and these are just 2 different levels of significance that you're looking at here, the darker being more a higher level of significance. What we see is, dependent on the bout lengths where the data is extracted from, gait will be sensitive gait will show a different pattern of sensitivity to discriminate populations. When we also think about how bout lengths are distributed and how we analyse our data, it's also important to note that if you only look at bout lengths that are 60 seconds and greater, then you're missing 97% of walking bout data. And given the previous slide that I've just shown you, you may also be missing sensitivity to differentiate disease. And at the moment, this area is particularly unclear in the research community, and it's an area that I think we need to pay more attention to. So that's my final point that I'll leave you to ponder on your way to the dinner this evening. Thank you for listening. I want to acknowledge my team, particularly Alan Godfrey, Sylvia Deldin, Alan Godfrey, and also Sue Lord and Brooke Gallner and Jill Barry, who've carried out the work that I presented today, and our funders.